In the next subsection, I want to discuss how you can construct the string matching automaton and also do that efficiently, not just any way of doing it. For that, I want to come back to the second type of automaton that appeared in the Slido question much earlier. That's the non-deterministic finite automata. And these guys, they look similar to the deterministic automata. If you draw them as such a state diagram, at first sight, they might look the same. The difference is that they're allowed to have ambiguities in what to do in a certain state. In particular, they are allowed to have no edges for some letters, which means if you end up in this state and you see a letter that you cannot process, tough luck, guys, you're doomed. But that means you must have had some other option earlier on that might have brought you somewhere else. Or your input is not in the language, so the automaton should reject. Then every possible way of moving through the state diagram has to reject. But the sneaky bit of the definition is it's enough if there is one way for you to find your way through this maze of states that leads to an accepting state. So it's at first sounds not very useful in an algorithm, but let's ignore that fact. For now, the nice thing about NFAs is that they're very trivial to write down for these kind of regular expressions. We can stay in the state 0 as long as we want. At some point, we commit to move forward and read the pattern, and then we can continue reading arbitrary characters. That's as easy as it gets, right? The automaton just expresses what we said in this regular expression before. Arbitrary things, the pattern, more arbitrary things. It's just not clear how you're supposed to know when to start your journey. And so the automaton says, well, that's not my problem. If you want to accept your input, you better find a way. But it's easy to write down. Cool. That's a non-deterministic automaton. And non-deterministic because it doesn't always tell you what to do, and you kind of have to magically explore all options. I carefully avoid to say you have to explore all options in parallel, because I think that's not quite true. It's not true to the nature of non-determinism to equal it with parallelism. It's not the same notion. So I try not to say it that way. But you're supposed to try all options. We can actually use this automaton for string matching. You have to keep track of all possible histories. But it turns out this is not that hard. It's not as hard as it sounds. Because what is a history in a finite automaton? It forgets everything about the past, but except for the point that the state where it currently is. So no matter how many different convoluted ways there may have been that lead to a certain point, it's all irrelevant if you reach the same state. All the rest of the past is ignored. So the set of all possible trajectories through the state diagram is at a single point in time as a snapshot is just a set of states. Previously, deterministic automaton, you were always in exactly one state. Now you're a bit more of a quantum guy if you want, but again, this is another analogy that's not perfect. But you can hover in this indeterminate state of being in several states. And until someone looks too close at you, you're undecided. Okay, again, it's not quantum. It's not in the quantum sense. There's no probabilities. There's nothing like this coming up. You can just stay uncommitted and stay in several states. You're happy to accept whenever the set of states that you're in at the same time contains an accepting state, a final state. I think this is much easier on an example than it sounds. We start in always state 0, so initially there's no ambiguity. If you read an A, well, let's look what the automaton says. I could stay here because A is part of the alphabet, or I could move to 1. So after reading the A, I'm simultaneously in 0 and 1. pick what you want. I'm not sure yet. Okay? If you read another A, you're actually staying in the same set because from 1, if you took this transition to 1 step ago, you would now be doomed. So that trajectory just ends there and is lost. But of course, if you had stayed in 0, you can again go to 1 or stay in 0. So you're again in the states 0 and 1 simultaneously. If you read a B from here, things get a little more interesting because from 0 with a B, you can only stay in 0. And from 1 with a B, you advance to 2. So you're now in state 0 and 2. If you read an A from there, things branch out further. If you're in 2, it goes to 3, and that's the only thing. The other option was you were in 0, but then you had 2 things that can happen. So you're now in 3 states at the same time. Then sometimes things sync up again. If you read a C, the 3 is lost, so that dies out. The 1 is lost, that dies out. The only thing that remains is the 0 state, and that can only loop. So after that, you're back to only one thing is possible. And you keep doing like this. So this is the same as before. We have seen these states already. A new thing happens when we're in states 0, 1, and 3 and read a B. In that case, both 1 goes to 2, 3 goes to 4, so we advance to 2, 4. And we stay in state 0 because in this case, we always stay in state 0. There's always this loop. From here, things get even wilder. So with reading an A, you branch out into 4 different things. It's really advancing the 4, advancing the 2, and advancing the 0 to a 1 and staying where you are. If you read a C from here, we already know that the 0, 1, and 3 will die out. We've seen that before over here. But the 5 can move on to the 6. That's how we made progress. Now we're in this state 0 or 6. And with reading another A, we reach a configuration that contains at least a final state. And so we can say, yep, found a pattern. And I don't even have to trace back which of these complicated histories that I'm all lumping together now led me to this point. It's enough to know if I reach this final state, there was one. And I know at which position the match ended, so I can subtract the length of P to get the starting position. All right? So that's kind of cool. It looks like the automaton contains no information that's helpful about the pattern, because it's literally just a pattern written on these funny lines, no other thought or input. But if you treat it as an automaton in this sense, stay in all possible states, and just maintain this set of states, you can actually use it for string matching. It's not a terrible algorithm. It's not the fastest either, because you have to maintain this set of states. And so I guess you can probably construct automata where the set of states that you're in is fairly large, and you would always have to at least check where each of these goes. So it's not quite clear if you can do this very efficiently, but the conceptual step seems to work fine. Now again, theoretical computer science has all solved it for you. There's a theorem, Nihil wrote, if you have a non-deterministic finite automaton, whatever the language is, could be ours, you can construct an equivalent deterministic one from that. It's called the power set construction. It's a standard topic in undergrad classes in automata, but if you haven't seen it, it doesn't matter too much. The programmers who have seen it will rightly object that while this is cool, it's an exponential blow up in the number of states. As the term suggests, you're basically creating a DFA using all the possible subsets of states. And that sounds really expensive. So he's already giving up. But luckily, some really smart people thought this through and discovered something. So there's an ingenious insight, and that's what also the KMP stands for that you've seen before, this first algorithm, or admittedly second if you want. string matching algorithm that we'll get to, you don't really have to apply this power set construction because the types of automata we're using are a bit special. To take that apart, let's see how we can go from a pattern where the last character is missing and add one more character and see if we can build the automaton inductively. So the idea is to start with essentially just the empty pattern, then the automaton does nothing. If you can do an inductive step where you can take the automaton for the first j characters, pattern p0 up to j, remember excluding, so it's j characters because we start at 0. If we have an automaton for that, maybe we can add the next character and build the DFA for the one bigger pattern. There's an easy bit. So let me draw the part that we have now, because this is a bit index mayhem. To show you again, so the pattern here is 7 characters long, but the automaton has 8 states. We start at the 0. And there's always, this is pattern character 0. So there's always the indices match between the state, and then the next outgoing right arc has the pattern character of the same index as the state had. So we have state j, and then there's a new edge labeled with p of j. That's the new character that we append. And we know where this leads to. It always goes to a new state j plus 1. So that's the easy bit. That's that part. Let's make that green as well. But we need more. We also need the case that when we're in the state j, which previously was the accepting state, right? So okay, let me go to the example again back. Here, the pattern has length 7. That means state 7 is the accepting state, and I don't need to worry what happens in that state because it always just had this loop. You found the pattern, happily stay where you are. If I add another character at the end, this changes, and I have to worry about what to do if I don't see the correct next character. So we now need somehow these links that go back. If I find a C that is not the same as the next character in the pattern. In language notation, people write this as this transition function. So delta of j and c means you're in the state j and you read a character c. That's just the target of these arrows. So how do we find out where to go with this? And you can't just always point back to 0. Then you would overlook cases. You can do examples where that happens. If, say, the patterns is just b, 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 if you were to jump back to 0, you would miss occurrences. The insight from Knuth, Morris, and Pratt is that we can use the construction of the automaton that we already have to help us out. And let me spell out a bit to explain this, what the transition function is supposed to do. And that's, remember this box from before that we've used. What is the meaning of a state? So this new state, if I go from state j and I read a character c that is not the next matching one, I'm supposed to find the longest prefix of this string, the pattern, the first j characters of the pattern, and this new character c added. I'm supposed to find the longest prefix of that, which is also a suffix of that same string, but with the first character removed. So I'm trying to look for I'm trying to look for how much can I shift the pattern to the right, but I want the smallest amount so that I still get matches. I want these things all to match. And so, of course, this will be a suffix of the same string. And stripping one character off is just to make sure that I'm not saying, haha, I keep the exact same string. It's a suffix of itself, so I'm not doing anything. To avoid that degeneracy, I'm taking one character off. Now, because that's definitely shorter, there's no way if you just see that part. Let me rewind. This still doesn't seem to help us much. But we know we have an automaton for the one shorter pattern, and it will have to react to any kind of string in some way, but we know in what way because we know what the states mean. So if we feed the automaton that we already have with this string where we omit the first character, it will have to end up in some state j. And that state, it will have to end up in some state, and that state will not be more than j. If it was more than j, it would be j plus 1, and that would mean that c is the next matching character. But we're in the case where that's not the next matching character. So what I'm saying here is if you feed the automaton that we have so far with these characters, it will not run into the new edge. It will stay in the part that you've already constructed. And so we can use the automaton for the part of the pattern that we already have to find out this longest prefix, because that's what the states there mean. It's a little convoluted. Let me see if I can. Okay, yeah, we have to go all the way back, but I'll show it on the example that we used before. Suppose we have this part of the pattern and of the automaton. So that would be A2, because we have two pattern characters already dealt with. And now the task is, say, to find the transition from this new state to when you read an A. Sorry, that's the easy one. That's this one. The interesting one is finding, say, with a C where we have to go to, if we're in state 2, which previously was this accepting state. And so what this tells us is round and C. So in this case, we have A, B, and then C. So we strip off the first character to go to P1JC. That's just BC. And now we simulate our green part of the automaton on just this part. And there's not too much interesting happening, but it goes 0, B, C. So it reaches state 0. And that's why the edge from 2 with the C should go back to 0. Okay? I know it's the first time where things get a little hairy in the details. The trick here really is you can use the automaton you already have so far, because it does the same thing you want, and the part you've constructed must be big enough for the part for what you need. So you can do this with all the mismatch characters, and then you obtain the next larger automaton. Now this still sounds expensive if you wanted to execute it, because you would have to run many times this smaller automaton, each time going through all these characters. And it turns out you don't even have to do that. You can be even smarter here. You can, if you do this on an example, it's easy to see. All these simulations of the smaller automaton, they start with the same characters, and just the last character is different, because that's the new mismatched character. So they all do the same kind of computation up to a point, and then there's one more thing where they differ. So you might as well instead do all these simulations together and remember where you landed, and then just do the last step for each mismatched character. And even smarter, you can maintain this state. So you don't have to start simulating from scratch. You keep that state and advance it with you. And I think this is so well animated in this video by from the book that we used in Unit 2 as well, that there's no point in me recreating this. So I'll just show you this snippet from the video. I'm not sure how well the audio will work, but let's try.
Let's take a look at a demo that does the full construction for the KMP DFA. So here goes. Again, one state for every character plus an except. Match transitions are easy. We build those. And we're going to start at position 0. And the mismatch transitions are easy. So now when we move over, X is, when we're in position 1 of the pattern, X is where we would be if we started out without that character, which would be the empty string. So we start out with just filling in zeros. For state 0, and we can do that without any further reasoning. But now we've got X initialized. So now what we need to do is fill in the mismatch transitions for state 1. So what are they? They're what would happen if we found those characters and we were in state X. If we found an A, we'd go to state 1. If we found a C, we'd go to state 0. And maybe you notice that's just taking the entries corresponding to the entries we need from X's column and putting it in J's column. That's all it is. And then we need to update X, which is where it would be if we matched a B. So we'll stay in, X will stay in state 0. So now let's look at state 2. So we need to fill in what would happen if we got a B and what would happen if we got a C. Well, it's what would happen if we were in state X and we got a B or a C. So all we do is move those 2 zeros over to column 2. And then don't forget we have to update X, and X goes where the machine would go if we saw an A, that transition from 2 to 3. So we just move X to state 1. So now we have X in state 1 and we're doing position 3. And now you can see how really simple the algorithm is once it gets going. So now the mismatch transitions are A and C. And that's what we have to fill in for column 3. But those mismatch transitions were already computed. That's where X would go. That's where it would go if we happen to be in state 1. So we move the 1 and 0 from column 1 over to column 3. And again, we update X. And when we see a B, X goes to state 2. And again, you can check what is X supposed to be. It's supposed to be where you would be if you started the machine on the pattern with the first letter cut off. So it's supposed to be where would you wind up if you got BAB, BAB, and that's a check. All right, so now it's straightforward. State 4, we have to fill in B and C. We go to X's column and copy over B and C from X's column. Then we update X. That's if you see an A, you go to state 3. Now we're ready for state 5. We've got X all computed. and we need to do A and B, and we get those from X. If it's an A, it's a 1, and if it's a B, it's a 4. It's just move them over. And then when we do the C and get the accept, there's no mismatch. That's we do update X to get ready, but when we get to state 6, we're done. And again, it's just as a double check, X is where you'd be if you saw B, A, B, A, C. That's the construction of the Knuth-Morris-Pratt DFA.
The key part here is you can maintain this state X where you would have been if you read the pattern that you're building the automaton for with the first character omitted, and that automatically takes you to the position just before where you should go. So this character, this position X, state X, is not what you put in the delta function, but from there you take one more transition, and the result there is what goes into the transition function. So delta, that was what is shown in this table here, right? And if you wanted to code this really, you see it's copying columns, so it's really easy to do this on an example, at least manually. The tricky bit is explaining why it's correct. Let's briefly discuss how well this works, even without showing detailed code for the construction. I hope that the video makes it clear enough how that code could look like. The matching part for the running time is as good as it can possibly go. You're looking at each position in the text, and you do a lookup for the DFA transitions. That's one table lookup. The time for building the DFA is a little less clear, but you can essentially do it in the time needed to produce the table. That's again, if you follow from the video, copying the column is proportional to the number of copied elements, and updating the state X and producing the new matching edge is also constant time each. So the total time is m times sigma. Sigma is the size of the alphabet, right? That's the number of rows in the table that you have. Plus n for the matching part. And the space is obviously what you need to store the transition function, so it's the number of edges. The matching time is really, really good. If the alphabet is not too big, also the overall time is as good as you can get because you need to read the text. But it is quite a substantial space overhead to have this factor sigma in there. And so for that, I looked this up in the break. If you use all Unicode characters, then sigma with the latest release is 149,186 characters, if you want to be precise. Now, that's quite a lot if that's a multiplicative factor for your pattern. Suppose your pattern is a few thousand characters. Now you multiply this with 100K. Now suddenly this is megabytes and megabytes of table, and most of the entries will be all zeros, because if your pattern's just 1,000 characters long, most of the 150,000 emojis won't occur in it, right? It's a bit of a waste of space and time to fill all this thing with zeros. Just because potentially the text could have all these emojis, but then you would still discover that the pattern doesn't have them. That seems wasteful. So in a way, if you can guarantee that the alphabet is small, or you don't have to worry about space, this is a good algorithm. But we're not completely happy yet in the general case.